Up until now, we've been looking at using electricity to make something move, which we call the motor effect. We also know, and I'll just give you a bit of history. The topic is going to be electromagnetic induction, but we know from a few experiments, and here are three pivotal experiments. In 1819, Hans Ørsted demonstrated that around every wire that carries a current, there is a magnetic field. And we know that this is a circular magnetic field, and we use our right-hand grip rule for that. Then this fellow, which you're going to be very, very familiar with, his name is Michael Faraday, he discovered that a current-carrying conductor in the presence of a magnetic field experiences a force. He's the one who discovered the motor effect. Okay? And he was the first person to apply that and make things move. But 10 years later, a little bit, not probably only about 5 or 6 years later, then he started to get his ideas together and he formulated it in the paper. In about 10 years later, he published his work about how he could use a magnetic field to generate electricity. So he's got this idea that if electricity can make things move, could making things move generate electricity? And 10 years later, he comes up with this idea of the ability to make electricity by forcing electricity to move or magnets to move near wires. Okay? So we're going to move on into looking at this idea. And if it wasn't for this one moment of our life, of our history, then our life today would be totally and utterly different. We don't have electricity. Now, do not take this down at the moment because this is going to come back many a times. We have to define a few things. So far we have got, there's only 3 parts in this course of this topic, the 3 laws. The 3 laws are the motor effect, which is a current-carrying conductor in the presence of a magnetic field will experience a force. The second is the one that you're about to see in front of you, which is called the law of electromagnetic induction, which says a changing magnetic field if that changing magnetic field acts upon a conductor, the conductor has induced within it an EMF. And the last is Lenz's law, which says that the induced current always acts against the motion. But we're up to this number 2. So we're going to have to define a few things. Whereas the motor effect, all the words that we use were quite known to us, this has a few things in it which are different. And the first one is the EMF, which we see just here. Okay? So let's have a look at, firstly, what the actual thing says. The law of electromagnetic induction says a changing magnetic field in a region near a conductor will result in electrical potential, also known as an EMF, across that conductor. If a circuit is provided, then a current will flow. So to work out what this means, we now need to work out what EMF is. So there's our first thing that was in that. So EMF, what is EMF? EMF, it's not normally with a capital E. When most of the time we do see it, we see it written as little EMF. And it has a symbol, and it's that curvy E from Greek, and it's epsilon. But you can do whatever you want. If you want to just do a normal E, that's fine as well. Everyone will know what you mean. So it stands for, EMF is three words, electromotive force, E, M and F. Okay. Now, it's the force on the electrical carriers, which we know are electrons. So when an electron, here's my electron, okay, if it's sitting in a wire, here's my wire, if the two ends of the wire are not connected in a circuit, if I push this electron with a force, will it move anywhere? So imagine if I put a force on that. Will I get the electron to move? The answer is no. the electron does not move anywhere because it's got nowhere to flow. The only way that an electron can flow is if I've got a circuit. And if I put a force on this, the electron can flow around, go through a battery, and up and around. Okay? So this force that is pushing on an electron but still doesn't make it go anywhere, that force still exists. And that is the electromotive force. It's a force on an electron that, if there was a circuit, would allow the electron to be pushed around the circuit. But often, there is no circuit, therefore it's like you pushing on a wall. Though the force that you are pushing on the wall exists, you can feel your muscles pushing, is the wall going anywhere? No. So the electromotive force is a force. It can't be really a voltage or a potential unless a circuit actually exists. But often it's easier to think of it as a voltage or a potential if we have a circuit. So it's often, we can also see it as a way of looking at voltage or potential difference. The only time, once again I'll say, once a potential difference exists, the electrons will be able to move, but only if a circuit is provided. So EMF is the push on electrons. These electrons won't go anywhere unless a circuit is provided. Okay? We know that if the electrons do move from a whole unit in the preliminary course, we know that as electrons move around the circuit, they lose energy, and that is called a drop of potential energy. Okay? So EMF is simply the energy that we can give to an electron if it was able to move. Okay? Are we okay with that understanding? Okay, so that's the first thing. The next thing, if we go back to our definition, okay? Now here is the Faraday's real law of induction. This is the one he actually wrote. The induced EMF, this is its law, but don't copy it down yet because remember, we are still working out the things in it. We've got that part. The induced EMF in a circuit is equal to the magnitude, to the rate at which the magnetic flux through the coil or through the circuit changes with time. So the first thing we have to define was EMF. Now we have to understand what is meant by this second thing, which is magnetic flux. Now we've already alluded to what flux is, so we now need to define magnetic flux. Now the HSC goes to a large amount of pains to distinguish between two different identities. The first identity is magnetic field. The second is magnetic flux. They are linked, but they are different concepts. And you need to be able to distinguish between the two. Okay? So let's have a look at what was meant by the first one. Okay. The first one is magnetic field. Yep. I've got to mention that. Yeah. Okay. Rightio. Now, I've got two titles up here, magnetic field and magnetic flux. Magnetic flux density is another way of saying the magnetic field. They are the same. Okay? Rightio. So we have to understand that if I say a wire is in a magnetic field and its value is 5 Tesla, what I'm saying is the wire is in a field which has a magnetic flux density of 5 Tesla. So, first thing, what is it also known as? The AKAs. Magnetic flux density is also the same as the magnetic field strength, which we know as the magnetic field. Okay. It is what we already know as being measured in Teslas. So we've already used this. Its symbol is B. Okay. What is new is this last statement. the number of field lines per metre squared. Okay? So, what we consider to be a magnetic field, we are describing it as a magnet. The magnetic field has a certain magnetic flux density. Now, let's unpack the words. What are flux? What is the word meaning in Latin? Flow. It means the flow. It is the field lines. Okay? So these are the field lines. And how far apart the field lines are, now these are field lines which are pointed in or out of the page? Out of the page, good, okay? So there are 16 field lines going out of the page. Here are 16 field lines also going out of the page. What can you tell me about the strength of one field compared to the other? Which of these has the bigger field, strength of field? This one over here is the strongest field, isn't it? Okay? Because they're tight. We already know that field lines which are closer together means the field is stronger. So magnetic flux density describes the magnetic field strength. Now, why, Catherine, did you say that this one over here was stronger than this one? Right, because the dots were closer together. There were a lot more dots per unit square. The area, the standard unit of area is the 1 metre squared, isn't it? So here I've only just drawn a very small bit of that 1 metre squared, but you can see there's a lot more, they're packed together, aren't they? So the more lines per metre squared, the stronger the actual field will be. Are we okay with that? Right, so that's magnetic field and it's described in terms of its magnetic flux density. Are we okay with that? So here we have a 1 metre by 1 metre. I think it actually is exactly 1 metre when I tried to measure this on this projection a few moments ago. It is a 1 metre by 1 metre square. Is the field going in or out of the board? Into the board. Okay? And how many lines are passing through this 1 metre square? Right, it's 15 times 15, which is 225. There are 225 field lines per 1 metre squared. Okay? In that case, this is a 225 Tesla field. Okay? Are we okay with that? Because the number of field lines that you can pack into 1 metre squared tells you the strength of the field in Tesla. That's its definition. Okay. So how dense are these lines? There are 225 field lines per metre squared. That's what we mean by density. These are lines of flow, field lines, therefore this is flux, the field line density. Equals flux density. So just getting all the terms used the same. Field line density, field lines is the lines of flux, field line density would equal the flux density, the same terms. Are we okay with that? Compared to the other term that we have to be able to use, which is magnetic flux. Okay? This is not the same concept as magnetic flux density. Okay? One has 3 words, one has only 2. It's another one. What is it? It's the number of field lines passing through a given set area of our own determination. Okay? I could say the area I want to talk about is 50 centimetres squared. Rebecca might say it's a field line, an area which is about 1 kilometre square. It depends on the individual circumstance of what we want to say. So it's a number of field lines passing through any specific area that you wish to determine. Okay? It's measured in Webers. It's like one of those, it's one of the units which has 2 letters in it. The other one I can recall off the top of my head is Hertz, HZ. It's a WB. It's named after a barbecue. No, it's not. Okay? It's named after a man called Weber, who invented the barbecue. No. Okay. And it's got a different symbol. The symbol is this thing over here, which is thigh. Okay? PHI. It's the letter that's in use in Greek. It's the starting letter for the word philosophy. A lot of our words start with PHI. Now, the Greek F sound, F sound, they don't have an F like we do. The thigh symbol is the F symbol. That's the reason why philosophy starts with a F sound, because these are the 2 letters in Greek, or ancient Greek, which were the same. We needed a letter for capital F for flux, so we chose thigh, big capital F, in other words. Okay? So that's the reason why it's that symbol. Now, to draw thigh, it's just a circle with a stroke through it like that. Okay? It's just 2 parts of the deadly hallows. Okay, there's no triangle. Okay? I know it's the other way around. Look, for God's sake. This is physics. It's not. Yes, dark arts. Okay. What is it? For defense against dark arts. Okay. Unless, of course, you're talking field lines. Okay, rightio. Now, here is a way of comparing the 2 concepts. A few moments ago, we drew this, well, you saw this massive big square, which has a 1 metre by 1 metre field, and there are 225 lines in here. So we know that this field in here is 225 Tesla. So the magnetic flux density, which is another way of saying the strength of the field, the magnetic field strength, is 225 Tesla. Because if you were to draw a massive big square of 1 metre by 1 metre, there'll be 225 lines in it. Okay? However, the difference between magnetic field strength, and magnetic flux density, and magnetic flux is here, right in the middle of it, is a random rectangle. And randomly, this rectangle has a specific size, but we can count how many x's are there in this. There's 1, 2, 3, 4, 5, 6, 7, 8 x's that direction, and 1, 2, 3, 4, 5 going down there. There are 40 field lines going through that rectangle. The number of field lines going through a rectangle or area or outline shape is the flux. So therefore the flux equals 40. Are we okay with that? If I made that rectangle bigger, would I get more flux? Yes. If I made it smaller, would I get less flux?
So they're both just the strength of the field, but one is you determine how big the area is, and the other is just the strength.
They're both measures of strength. Sorry, one is measure of strength, the other one is just number of field lines. Okay?
Wait, say that again.
One is the number of field lines in a 1 metre square, the other one is the number of field lines in whatever you decide.
So
One of them is the definition of the strength.
So with flux density, that's just how many is in 1 metre squared, and then flux.
Flux is just how many is in your rectangle. Yeah, exactly. Okay. Right, yeah. Now, going back to this, that 40 is 40 watt, not 40 Tesla, 40 Webers, yes. Okay. Now, this is quite important because we're going to be talking about change of flux in a few more moments. Change of flux is not change of flux density, it's change of flux, which is the number of field lines in the coil. So here, the magnetic flux through that is 40 Webers. are we getting the difference between flux and flux density? Okay? So, taking it this one here. I'm telling you that if you were to draw a metre squared here, let's give me a nice big red. Yeah. There's one. Around do that. Yeah, so it was meant to be that one. If I do a nice big 1 metre squared, now 1 metre by 1 metre, and I count the number of field lines inside this 1 metre squared, I am saying that there is 100 field lines. So the strength of this field here is 100 Tesla, which means in 1 metre squared there would be 100 field lines. So there'll be 100 in here. Okay? What the number of field lines that you would find if you could draw a 1 metre by 1 metre gives you the strength of the field. It's how we all standardise the measurement of the field. So the 1 by 1 metre gives us a standard way of measuring the strength of the field.
What if the field's not 1 metre by 1 metre?
You just have to use common sense and do a mathematical. What would it be if it was able to extend by 1 metre by 1 metre?
Yeah.
Okay? Right. Now, if we then look over here at this one, and I'm telling you that even though this whole field out here is 100 Tesla, because this is a smaller rectangle, will we expect to have less lines through this coil or more lines? Less. And I'm telling you that if you count them, there are 70 in there. It doesn't change the fact that it's still in a field which has 100 crosses for every 1 metre squared. It's just that because I've got a smaller rectangle, I have a smaller number of crosses going through it. I'm telling you there are 70, so therefore this here is 70 rivers. Okay? Getting the difference between the two. Good. Okay. Even though it's different, the two concepts have to be related somehow. So have a look at this one here. The area of this coil is 4 metres squared. Okay, it doesn't exactly look like a square, but that's the projection. And inside it, there are 36. So what's the field strength? No, think about it. The field strength. Field strength is the number of field lines per metre squared.
18.
Right, so for 4 metres squared, there would equal how many field lines? There are 36. So in 1 metre squared, there would equal 9. 9 field lines per metre squared means that this field in here is 9 Tesla. Okay. So if I was to divide it into 4, that's now 1 metre by 1 metre. And that means in every square of 1 metre squared, there would be 9 flux flow lines. Okay. What's the flux through the coil though? The flux through the coil, or remember the coil is, when I say the coil, the shape is what I'm saying here, because eventually these shapes are going to be made of wire and they're going to be the coils. The rectangle contains how many? 36. So this is the magnetic flux density, which is the strength of the field, is 9 Tesla. But the actual flux, the number of lines through the coil or through that rectangle is 36 Weber. Are we okay? Are we getting this concept? Right, yeah. So now we know that they are related. The number of field lines through a rectangle, so if I had a rectangle, here's my rectangle, and I'm putting it in a field. Okay? If there were more X's behind that field, would I get more lines through my rectangle? Yes. So if I put an extra X between each of these, would I get more X's inside?
Yes.
Yes. So the number of, remember phi here is the number of field lines in that rectangle. it's proportional to the number of field lines that exist actually behind or through the coil, isn't it? So if I was to place this into a strong field, I'd get more flux lines. Weak field, less flux line. Also, if I was to make this rectangle smaller, what would happen to the number of field lines? It would decrease, wouldn't it? So if I was to increase my area, I get more field. So field number of flux lines is proportional to the amount of area of the coil. When we have two proportionality statements like that, side by side, we can make an equality statement out of it. If they're proportional to that, it would equal to that times that. The K would be the constant proportionality to make it work. But if we choose our units correctly, if we measure B, the field density, in terms of Tesla, and A in metres squared, then K is chosen nicely to be what number? 1. And therefore you get that. Okay? So the flux is equal to the field strength times the area. This formula does not exist anywhere in the on the sheet. It's not exactly that you have to use it, but it is handy every now and then for use. Okay. So let's just check that our formula works. The field that this is in has a strength of 100 Tesla. That means that if we were to use a 1 metre square, we'll be able to count 100 lines going through that 1 metre square. If this area over here is half a metre squared, remember area has to be in terms of metres because it's that K and constant proportionality equaling 1, then how would we work out the flux? Well, flux would equal 0.5 times 100, which means there'll be 50 lines going through that square or rectangle or whatever shape it is. If this is a circle, it wouldn't matter. Okay? All I have to know is the area of this shape, whether it be an octagon as well. It doesn't matter, and that's very important later on. The shape becomes irrelevant, it's the area. And thigh is measured in meters. Okay? That makes sense? Easy way of doing it. Okay. I won't do that slide at this moment. Okay. We'll now go to the next page over, which is beginning Faraday's law of magnetic induction, and then we'll leave it there until we come back. So I'll show you a demonstration of how he came up with this idea. So this, on page 18, is a differential equation. You'll see it as epsilon equals minus m with phi over dt. Okay? And I've got to come up and show you why that or how that works. To do this, we come to Faraday's statement. So let's think about what he was trying to say of how to generate electricity. He says,
Is this one question 3?
no, just that's where we'll no. I'm going to show you in a few more moments the actual experiment. So it's just this will go in the page, just so you know where it's going to go to. In a few more moments, you're going to see all that thing now. That you'll copy into that position. So you're not going to have to do that yourself. Okay. So let's go back to this. Okay. Remember, the whole point is to get us up to understanding this statement. And I'm going to give you a better one. This is the one that he came up with. I'm going to give you a much better one to memorise, which is something like a conductor in the presence of a magnetic field will have it produced within a EMF. Okay. So the induced EMF that is made, that's the electricity. So we now know what EMF means. EMF is voltage if a circuit is provided, is equal to the magnitude, the size, at which the magnetic flux through the circuit changes with time. Now we know what this means. Magnetic flux through the circuit, circuit meaning a coil, if I can change that, then I get electricity inside my coil. So I have a coil of wire, a rectangle. Here's my rectangle, and it's made of a conductor, like copper or something like that, so that it can have electricity flow within it. It creates a circuit, okay, so it actually has ends which join up. All I need to do is change the magnetic flux somehow. And I'm just going to very rapidly go through a few methods that we can do it. How can we change? Don't copy it down, you can copy this next time. We can do a few things to make the magnetic flux change. Remember, all we need is we've got a rectangle here, and I need to have magnetic field lines go through, and then have either more or less magnetic field lines through. Okay? So if I make more dots appear, and then less dots appear, I change it somehow, I get electricity. So, what's one way? The first one here is turn the field off or on. Imagine if you could just turn the field off from behind it. Okay? What about if that was an electromagnet? I increase the knob for the electricity, make it go zoom, and I get lots more X's, or much more dots. Do I get more? Have I changed the number of lines going through my coil? Yes. This one's a bit of a furphy, but decreasing the size of this coil. This coil is actually made of metal, so it's not very stretchy. But imagine you could stretch it or shrink it. That would make the area change, wouldn't it? We could take a magnet and move it closer or away from this coil. Okay, now I'll explain why that does in a few moments. And the best one of all, we can turn the thing in the field. If we make it like a little ballerina, and here is my coil, and I turn it like that, then sometimes if the lines are going this direction, there's no field lines going through me now, is there? Lots going through me now, none now, lots now, none now, lots now. For the people at home, I'm just spinning around in a circle. Okay, so these are the ways, and we'll recap them next lesson. But removing, the biggest way is this one. That's the one about the coil, because the magnet and the coil, because if you move the ends of a magnet have the lines very close together. As you go further and further away, the lines start to spread out because of that pattern. But the best one is spinning the thing. And that's how we do it in the real world. All of our generators, we just take a coil and we spin it. And we just got to have a permanent magnet somehow. Okay. Rightio. So we'll stop there. And we'll take it up the next lesson.